yeah, let me thank the organizers for this great opportunity to speak here. Patras is always a great workshop to go to, but it's obviously much nicer to see everyone back in person. And yeah, so the work that I'm going to talk about today has been done in collaboration with these people. And well, I mean, from the title you can see what it's about, but since it's one of the few talks that touches on the cosmological part of things, let me maybe say what I'm not going to talk about. There's been quite a bit of work on the sort of thermal axion production, both for QCD axions and axion-like particles. But just to make it clear from the start, this is going to be exclusively about non-thermal production. And if you look at, well, a variation of the plot that we've looked at so many times at this conference, here we can see the axion or axion-like particle constraints in the mass and photon coupling plane. And this is more the sort of cosmological part, so we can see the sort of typical mass scale are mega-electron volt, and we can see constraints from auxiliary constraints also from astrophysics, so from stellar evolution and globular clusters, supernovae, and then a bunch of cosmological constraints. And if you look at the plot, you might see, well, you might say, well, it's not really interesting to look at this. I mean, it's all excluded. Why do we bother? But one of the things that will come out that, you know, if you extend the parameter space a little bit and think about more generalized models, then you can free up some parameter space, and that will be sort of one of the main conclusions of the talk. But perhaps just to more generally motivate why you want to do what we call these global analyses. So on the left-hand side, you see some sort of model, and what people typically do, of course, is to overplot constraints from different experiments, and that's, of course, all fair and good. But what you have to keep in mind is that all these experiments make, you know, different assumptions, and sometimes they may be even inconsistent. And in particular, what you can see on the right-hand side is that if instead you actually combine the underlying likelihoods, so the actual data of the experiments, is that sometimes you can get slightly stronger constraints here, or if you have some sort of correlation between the likelihoods, then you can also get weaker constraints. So it's a more, let's say, complete, rigorous method to combine these. And if you want to do this, it's if you also want to look at more multiple parameters or more parameters, it's important to keep in mind that, you know, sort of just randomly scanning the parameter space is probably not going to do the trick, because as the number of dimension of your problems grows, yeah, this is inefficient. And if you want to do a statistical interpretation in Bayesian statistics, say, then it could also be completely wrong. So yeah, so this is sort of the rationale for why we want to do these global fits. So since it's been a while that I've presented global fitting results at this conference, yeah, let me start, or in the next part, I'll just say something about global fits with GAMBIT, and then I will basically say a bit more about our setup for this particular study, and then you know, summarize our likelihoods, constraints, and overall result. So just again, to recap a little bit, what are global analyses for? So basically the general idea is that we want to include all the information that we have with all the data we have, so that we can, you know, draw the most informed conclusions, and there are, of course, some caveats to that. Yeah, and I will come to these in a second. And most analyses, you know, in high energy physics are done in classical statistical frameworks, so frequentist analysis, but as you are aware, in astrophysics or in cosmology, a lot of people prefer the Bayesian framework. So our approach is usually to do both analyses and see, you know, what kind of conclusions we can draw respectively from these analyses. And you know, as new data is coming in and we learn more, and you know, we maybe want to look at more complex model in the future, the sort of main selling point of GAMBIT, I guess, which stands for Global and Modular Beyond the Standard Model Inference Tool, is that you have a modular framework, which means that you can easily plug and play. You can sort of plug in different likelihoods and you can extend it. And I will also come to examples of this in a second. So what you have to do is to basically define a model in terms of some phenomenological parameters. In some cases, write the functions to compute the observables. In other cases, there are already existing tools, either within GAMBIT or some external codes that you can connect. And then basically, you need to have access to the likelihoods. And then basically everything else is done by the sort of machinery. And again, I will get to that a bit more detail in a second. Right. Now, this is not from our study. This is from a more complicated study of an MSSM model. But it's sort of to illustrate, what happens when you connect all these different pieces. So the likelihoods, the model calculation, and what GAMBIT essentially does at the start of your scan, it will figure out the sort of order of evaluation, right? Because if you want to, if you want to compare, say, to Planck, you want to compare to the observed density of that matter in the universe, you first need to calculate what your model predicts, right? So the software figures out, that you have to do this first before you can plug it into your likelihood. And the user can impose certain rules, and basically you have several options. Say you prefer one theory code over another, and this is all respected by the software, and that is one of the things that I mentioned before. This ensures the consistency of your analysis. Right. And yeah, so the sort of message there I also want to basically send out is that if you have a nice theory code that could be helpful with some of these global fits, we're always very happy to have your code and to backend it and to basically write a wrapper so that it can be used in future analyses. And we've studied not just Axions. So if you say, okay, I'm here more for the WIMPs, there have been also studies about WIMPs, about SUSY. We've also reacted to the Xenon one-tonic CES. And we typically try to make as much as possible available on GitHub or Zenodo. So obviously the software is on GitHub, and samples or the evaluated likelihood functions should be usually available on Zenodo. And here you can find a link to kind of a more complete set of papers that have been studied. Since I'm an Axion guy, I just want to sort of mention or give an example from previous work from one of my own studies in which we looked at the pre-inflationary scenario and did a sort of classical likelihood analysis, so did a combined scan of all these likelihoods, and also looked at the sort of Bayesian picture because in that scenario you have a random initial angle or field value that has we've talked about before. So basically you can implement this in this Bayesian paradigm to highlight the most sort of or get the most probable regions for your parameters. Now, just as a sort of side remark, I mean one of the criticisms that you usually encounter is that these Bayesian analyses have a sort of prior dependence, and this also afflicts, for example, the E/n ratio that ties the axion mass to the coupling. And what I've done, or mostly my master's student done, my former master's student Weishak, is to catalog for the KSVZ case all the theoretically preferred models in the definition of Delusion and others, thanks that you can see here. And to basically, from this catalog, you can also come up with more physically motivated priors for this E/n ratio, so that sort of takes care of some of the issues of this. Now, why did I talk about this? Sorry, other than okay, I can use the other than shamelessly plugging the previous work, it is also to tell you that we've already sort of started implementing axion and ALP models in GAMBIT in a sort of hierarchical manner. So you have what we call the general ALP model on top, which you see a few of the sort of standard couplings, and derived from there you can make more concrete realizations of different classes of models. And so for this study we've basically extended the previous work to also include things like the reheating temperature or the total non-thermal abundance of these particles, and I get to that on the next slide. I'm going to basically talk about this model that we used in the study in more detail. So as I said, these global fits are sort of, in some sense, ideally a black box scenario. So what you want to do is you want to put everything together, go away for 2 days, let it run on the cluster, then you come back on the computing cluster, then you come back and you get your results. But of course, you also kind of want to understand where these, especially the non-trivial correlations come from. So for these initial studies, it's usually useful to restrict yourself to a simpler scenario where you can, where you can understand the results more intuitively instead of, doing the full blown out, complicated model with many parameters to begin with. So what we focus on here is ALPs that only couple to E dot B. And we also don't consider some sort of mass dependence. So in the full model, we have parameters that, for example, for the QCD axion would parameterize when the mass becomes constant and what sort of the temperature dependence of this mass is at high temperatures. And if you look at, or if you think about all the sorts of different non-thermal creation mechanisms that you can get, you think, of course, about the realignment mechanism, but you could also have a freezing contribution. And the sort of issue with realignment is that, you have sort of 2 more parameters in the most general case that describe this. And also with the freezing, you can see that there are some degeneracies here. So to better sample or look through the parameter space and do this analysis, we decided to essentially fix the reheating temperature to some low value, and to, instead of basically calculating both realignment and freezing, to only calculate the freezing contribution and use the total non-thermal abundance as a free parameter. As you can usually, in classical statistics and frequentist statistics, you can, if you can avoid constraints, right, you will, by profiling over your results, you will go there, right? So this is sort of the logic that allows you to simplify these models. And so with the final parameters that we look at are the ALP mass and the lifetime, which is basically interchangeable with the coupling, and the total non-thermal relic abundance in absence of decays. But of course, we include decays in our estimate. So just to say what how we calculate the freezing abundance. So here we use micromegas, and here on the plot you can see how this changes as a function of mass or the heating temperature. And in particular, the solid lines are the results from the micromegas code, and the dashed lines are sort of naive approximations where you add like Boltzmann suppression factors, and that sort of like in the approximate formula that I showed earlier, and you can see that they agree very well. And as I said again, the reason why we calculate these is to make sure that yes, we allow the non-thermal abundance to be a free parameter, but we don't want inconsistencies by at a certain parameter point having a value that is in conflict with the unavoidable freezing contribution. Right, and then on top of that, of course, since we're dealing with cosmology, we look at the standard cosmological models, and so in total we have 12 parameters, the 3 ALP parameters I just talked about, 6 lambda CDM parameters, and then there are a couple of experimental nuisance parameters and the neutron lifetime for BBN. Right, and conventionally what you usually say is that you cannot really do anything after BBN, but in fact, and that's sort of one of the takeaway messages later on, is in the case of non-thermal dark matter, you still have some sort of wiggle room in sort of shortly after that. And also in some previous works, there's been some speculation about maybe ALPs being able to solve the lithium problem, which is basically concerns the difference between the observed, or the estimated, and the theoretically predicted abundance of lithium in the early universe. And so we end up with this sort of region of interest where we might be able to address this problem and not get in conflict with these constraints. And then basically we just need to go back to the plot and think about what kind of likelihoods did we see there on the plot. And here's basically a list of likelihoods that we include from Planck, so CMB measurements. So usually when you think about Planck or the CMB measurements, you only think about the anisotropies. But actually, for these decaying particles, it's really interesting also to look at the shape of the CMB spectrum, which, as you know, is to a good approximation a black body spectrum. But actually, there are some it's possible that you have tiny deviations from red due to energy injection in the early universe. And the last time that, the CMB spectrum was measured to some accuracy is more than 20 years ago in Kobe with the FIRES instrument. And these constraints, as we will see later, will also play an important role. And of course, we could have neglected some of these likelihoods from the beginning, as they only sort of marginally affect the results, and that would have, simplified some of our calculations. But the sort of logic of global fits is that, maybe we've missed something, we didn't think about something, and since it's not really computationally much more expensive to also include the effects of delta N effective and some structure formation constraints, we just included them. So maybe from all of these, let me focus on the spectral distortions a bit, because it's something that's perhaps not discussed much in literature. So as you can see, there is a very tiny amount of spectral distortion. So these are the error bars from the measurement, the gray shaded region, that would be allowed across different frequencies, and depending on the ALP lifetime, you inject more or less energy into the spectrum. And since we are doing this in a sort of unified framework, we don't do what has been done in the past, namely look at particular types of spectral distortion. So some that affect the chemical potential, for example, which, for example, in this case, you can see that as the ALP lifetime goes up, the so-called mu-type distortions sort of start to increase at lower lifetimes already, but they never reach sort of the limit as they fall down later on. However, if you combine them, or if you look at the combined amount of spectral distortions, you do already get a limit here, right? Whereas, if you only looked at mu and y-type distortion separately, you would think that the limit on the lifetime is much higher, because only later on, or for higher lifetimes, would you get a limit directly from the y-type, another type of these spectral distortions. Right, so let me remind you, so this was our region of interest for the parameter scan in the exclusion plot that I showed you before. And if you do sort of let GAMBIT do its magic, what you find is that basically you do have a region, this region that is allowed for the non-thermal ALPs in this work. So basically, thanks to the opportunity or the not fixing, having basically the abundance as a free parameter in this work, and you also find a unique best fit point. But before I get to that, of course, once you have these results, it's very convenient to project them into different planes, depending on what kind of analysis you did. So, for example, this is a profile likelihood analysis, and so if you look at the tau and the abundance plane, then it's quite easy to understand that here really the cosmological constraints play a role, since the abundance plays a role here. Whereas if you look at the more traditional mass and coupling plane, you have kind of no loophole, so you can't go to regions of low abundance, but really, these are very solid constraints here from astrophysics. So, depending on which parameterization you look at, which is quite easy to do once you have the results, you can see that your results behave as expected. So, what about this best fitting point? Did we detect ALPs? Well, I'm afraid no. The reason why we have this unique best fitting point is that indeed we do improve over LCDM slightly by basically due to photo dissociation. We can improve the predicted deuterium over hydrogen ratio, but keep in mind that this is only a very low significance, and it also, as it also doesn't help with the lithium problem, so it's also not really appealing from that point of view. And we also did a Bayesian analysis to kind of look at this further, and also here we find that we looked at different prior choices, two different prior choices, and in both cases the odds are against the extended model, so the LCDM plus ALPs model. So yeah, in summary, this is really not a hint. This is not to be seen as a hint for ALPs. As the model, although there's a few new parameters, is basically too complicated compared to the very marginal gain that you're getting. And yeah, that basically is the main message that I wanted to get across. So I hope that I could convince you that GAMBIT is really a well-suited framework to, well, for not just for global fitting, but for continuously extending our knowledge about the parameter space to look at more complicated models and include more newer data as they come in. Heavy ALPs are still viable in cosmology, so hopefully at the next Patras Workshops I will not be the only person talking about this. Yeah, so even though I said this best fitting point is, it's not statistically significant, there is not a discovery, there are missions that are being discussed, so the spectral distortion missions, if they will be realized, will be able to conclusively also get rid of the parameter space that we've shown is still viable, and in fact also the spectral distortions are the reason that the lithium problem cannot be solved, because an earlier study where this was sort of speculated or thought about didn't include these constraints. So yeah, since I think this, I have a few more backup slides, but I guess I will, that's all the most important stuff I wanted to say. So I think in order to bring this to a quick close, I will yield my time and take questions. Thank you.
We have ample time for questions.
Thank you. And I have a question about the way you computed the spectral distortion. Mm-hmm. Did you compute just y and mu through the usual window functions, or you did something beyond? I missed this point.
No. So basically, what we used is we used the class and Monty Python interface. So what they do is basically, so this framework, they can do kind of with the Green's function approach. They can use the full machinery to do the complete, set of spectral distortions, not, classified in some sort of type. So that is possible, but it is. They have different approximation schemes, and we use one which is very close to the full result, but in fact does use, it sort of splits everything up into sub-Green's functions. So, but it is basically, it is consistent with the full result, and in fact, we don't just do the individual ones. Yeah.
More questions. So let me ask a question. Mm-hmm. So what's the interpretation of the profile likelihood from the point of view of the theory side? Many of the couplings are, of course, unbounded from below.
Yes.
And are you inevitably going to generate contours that are just around the corner in terms of observability? Right. So maybe first to the interpretation. So, so the classical statistics approach, or the frequentist approach, is basically asking the question. If from your theory side is basically the question you would like to ask, or that you would like to answer, is, can my theory hide somewhere? And this is precisely what the profile likelihood is doing, because it's always trying to, or it's sort of projecting down by maximizing or finding points that maximize the likelihood. So in that sense, it's always trying to sort of, if you have a 2D plot, it's trying to assign the other parameters to some values where basically you are, it's as good as you can get. So it's basically answering the question, where can my theory still hide? And sorry, the second question. In that sense, it's always just around the corner, or is there something more complicated? Right. So yes, it's but you can, for example, as you've seen here, you can do a direct comparison in the frequentist framework as well against lambda CDM alone. And if the new parameters
if the new parameters basically don't improve the fit at all, or if it's the same as LCDM, then basically you would, the p-value would tell you that you should pick the simpler theory, and you can also do, a Bayesian model comparison again with the prior dependence, but that will give you a direct comparison again between the old sort of the LCDM or some other alternative theory and that one. And so in that case, it's not just, from the plots, I agree, but you have to also not only look at the sort of parameter estimation, but also the model selection. So they both you have to do both things to make a statement, right? And unfortunately, the parameter selection, model selection is not something you see from the plot, right? So these are two separate steps. Yeah. Thank you.
Thanks, Sebastian. Is there an intuitive or phenomenological sort of explanation why the global fit seems to prefer a 100 MeV ALP rather than a 1 MeV ALP?
Right. So maybe let me go to. Right. So. So basically, so first of all, you're being pushed down a little bit here by the astrophysics constraints, which, as I said, you can't really avoid, especially in this projection, right, because they are there. And then basically, you do have to take into account the spectral distortions. And basically, if you, move up in this sort of region here, you can't avoid these constraints by because you will have this irreducible Friesen production. So you can't go to zero, you will always have axions around that are decaying sort of the wrong time. So basically, this only pushes you to this region where, you can push down to very low non-thermal abundance, and basically, if you don't have anything there, it can't produce gammas, it can't photo-dissociate things, it can't produce spectral distortions, and that's the main reason, right? So if you, if you had a more concrete model that predicts, the radial density, and of course this picture would change. But from this point of view of asking where can my theory hide, if you leave the option open of going to low abundances, say for the Friesen, you will be pushed to that region, if that makes sense.
Thanks.
Yeah.
Can I?
Or maybe
Friesen abundance. At that once you get above a certain mass, the Friesen abundance is Boltzmann suppressed because you fix the reheat temperature to be small. So if the mass is larger than the reheat temperature, Boltzmann suppression.
So this is a 5 MeV. Okay. This is all for a low reheating.
Yes, because usually you avoid things by going to that reheating temperatures, but we're also looking. We're also making sure at the moment that this is not an artificial problem. But usually we pick this because this is how you can usually hide your problems. Yeah.
Thanks. Can I very quickly ask one more question? Very quickly. Okay. The graph theoretic solution to the dependency tree. Sounds like it could be very useful if one experiment or one probe detects like a signal. What are your thoughts?
The solution to?
The graph theoretic solution to the dependency tree.
Yes.
Sounds like it will be a very useful thing if tomorrow one experiment or one astronomical probe says we have a signal.
Right. For the graph theoretical problem, it's not necessarily the optimal order of evaluation, right? It's just a sort of possible one that makes sense, but we also have some features built in that say, for example, because some calculations are more expensive than others, right? So basically, you can assign a label to your likelihoods, like this is a hard to compute likelihood, this is easy. So it will, the code on top of finding a good possible solution will also try to start with the easy stuff. And if your likelihood is so low that there is no point in calculating the other stuff, it will not do it. So there are some smart features, and so for bump hunt, for the sort of excess hunting, ambulance chasing, it's quite useful that it's optimized in this way. Right?
Thanks.
Yeah. Okay, thank you, Sebastian.